Okay, so all we can do to begin with is just recap some of the bits that we did last week. So we'll take it in turns to answer. So, Jemima, first, describe the term antagonistic muscle pairs. What does that mean?
The muscle that's relaxed during a movement.
So the antagonist is, what am I talking about when I'm saying antagonist pairs, when I'm talking about both of them?
Oh, bicep, tricep, hamstring, quadriceps, gastrocnemius, tibialis anterior.
Good, perfect. So all those pairs that work together with one being the working muscle and one being the relaxing muscle. So then, describe the role of the triceps in a press up. Just giving you a tip, think about both the upward face and the downward face. So what do the triceps do in a press up?
They're the ones that are working, I think.
On the up or the down?
On the down, they're not working.
What does a tricep do? Think about it. Which, does it bring the bone closer or further away from it?
Closer, so
Closer, so it must do extension. So it must be the agonist in which phase? Up or down?
Down.
Down, yeah. So it's an antagonist going up and the agonist going down. Jemima, describe the movements that occur at the hip during a star jump.
Abduction and extension.
So it's going to go out and back in. So you got the first one, right? Abduction, and then it's, what's the opposite? Adduction, yeah.
Sorry.
That's right. So then, give a sporting example of extension at the elbow. Anything you like.
Probably tennis if you're going like to hit it.
Good, so we in the preparation we've got flexion, and when we do the serve we've got extension. Well done. Right, describe the movement created when the gastrocnemius contracts.
Flexion. No.
Something
Yes.
flexion.
Plantar.
Good.
Yeah.
Plantar flexion. And what about when the tibialis anterior contracts?
Dorsiflexion.
Dorsiflexion, so just the opposite. So then, state the largest muscle in the back.
Is it the?
It's got a long name as well.
I remember this one.
Do you need help?
Yeah.
Go for it. Good, latissimus dorsi, it's a big muscle in the back. Jemima, in order to take a penalty in football, a player will swing their leg back in preparation. State the term used to describe this movement and the muscle that is responsible for it. So it's swinging the leg back.
Extension.
Of the
hip.
Good.
The gluteus agonist.
Good, well done. What's the antagonist?
The hip flexor.
Well done. So then, state and give an example of 3 types of muscle.
Flat, long, and short.
Are they muscles?
Oh no.
What are they?
Fine.
Good, what are the muscles?
Types of muscles.
Some you choose to move, some you don't choose to move.
Oh, cardiac.
Good.
Involuntary, involuntary.
Good. So the cardiac is
Heart.
a voluntary muscle. Give any example.
Bicep.
Yeah, and what's involuntary muscles?
The
Where are they
ones
found?
that we can't like control.
Perfect. Maybe like in our digestive system or. Jemima, what is the difference between a tendon and a ligament?
The tendon is attached to the bone, and the ligament is attached to the bone joint.
I think I know what you're talking about. One attaches muscle to bone and one attaches bone to bone. Which one attaches the muscle to the bone?
Tendon.
Good, so tendon is muscle to bone and ligament is the bone to bone, so it stabilises the joint. Okay, so this is the last little bit that we haven't actually quite done yet, and then we're going to move on to the cardiovascular system today. So the last bit of the muscular system was muscle fibres. So when we think of a muscle, we generally just think that's our muscle, but we need to know how that muscle is made up and how it works. So inside a muscle, there's hundreds of thousands of muscle fibres, and it's those that will contract. So every voluntary muscle is made up of lots of muscle fibres. And then each fibre contains myofibrils, which are strands that grab onto each other and pull to make the muscles contract. So if we just look at this picture, so we've got the muscle fibre here. So here's our muscle, and inside it is loads and loads of muscle fibres. Then we've got a muscle fibre, and then inside the muscle fibre is myofibrils, and it's these that will contract and pull on each other when it physically contracts. So when you need, if this comes up in exam, all it might ask you to do is to label a muscle fibre, and maybe it might ask you to label the myofibrils. It won't really ask you to do anything else, but it's just having an understanding that a muscle isn't just a solid muscle. there's lots of bits inside that muscle that will help it contract. Okay, alongside that we have different types of muscle fibre. So in every muscle we've got lots of muscle fibres, and they're different muscle fibres inside it. So we've got, sorry, it shouldn't be fast, it should be fast. So we've got fast twitch and slow twitch. There's two types of fast twitch. There's type 2A and type 2X, and then slow twitch is type 1. So looking at these, our type 2A is anaerobic work, so it's like a 100-metre sprint would be our type 2A, so it's our fast twitch. Type 2X is also anaerobic work, but it creates a much greater force, so it's a really quick, powerful force, like a shot put. So it's really short, so we don't have lots of type 2X, they don't have loads of energy, it'll be really intense, strong outbursts, and then it's gone. Type 2A is for a 100-metre sprint. And then we use our slow twitch muscle fibres for low intensity aerobic work, like a marathon. So our slow twitch fibres can work for longer periods of time, but they don't create as much force, whereas these create the most force and tire out really quickly, and these create a lot of force, but in a fairly long distance. We can do that for about 60 seconds, so that's a bit longer, maybe not even 60 seconds. And we all have different types of fibres, so in both of us we'll have type 2A, type 2X and type 1, but you'll have different amounts, so everyone has different quantities, and that's based on genetics. And it will depend what type or what quantity you have of each, which event you'll be best at. So if you've got lots of type 2A, what type of sport would you be best at doing?
100-metre sprint.
Yeah, and if you had lots of slow twitch, anything that's endurance, so it might be cycling, it might be running, it might be swimming, but more endurance based. So which muscle fibres do you think Mo Farah has the most of, and why?
Who's my father?
Do you know?
I know.
Go on and answer this one, you do the next one.
It's the
Tell
longer one, the XL. I think.
Type 2 is the fast twitch and type 1 is the slow twitch.
Type 1.
Good. Why will he have more type 1? Who is Mo Farah?
He used to do track running and he was really good. Now he does road running.
Now he does marathons, so he's a long distance runner. He's part of Team GB.
Is he
And-
the one that does the thing?
Yeah.
No, that's
Yes.
Usain Bolt.
He does this one and Usain Bolt's this one.
Yeah.
Talking about Usain Bolt, which muscle fibres do you think Usain Bolt will have more of, and why?
The type 2
Type 2 what?
A,
A.
I think.
Do you agree?
Yeah.
So he needs that type 2, the fast twitch, but it's not the all
Really,
short,
yeah.
powerful. What about lastly, which muscle fibres do you think Cristiano Ronaldo has more of, and why? Do you know who that is?
No.
So he's a football player. So any football player, doesn't really matter who. What would a football player need more of?
A bit of both.
Why?
Because like he might do
Because you-
a quick sprint, but then he needs to be
How
able
to
to
kick the ball.
keep
Good.
doing he needs to be able to do like more than one. He
How long
needs
does
to
a
have
football match last for?
90 minutes.
That's a long time.
Oh.
So 90 minutes, so he's got to have, it's fine. He's got to have slow twitch because he's got to last for 90 minutes, but he's got to have type 2X because when he's kicking that, maybe a penalty kick or if he's gone up for a header, it's really short and powerful. But he's also going to do lots of sprints, so he needs a mix of all of them.
Let's have a quick recovery.
Magic
Does.
sponge and some oranges at the break.
He's everything. So we're going to move on from the muscular system. So that is the end of the muscular system. We'll come back to that when we look at what exercise does to the muscular system. But today's lesson is all about the cardiovascular system. So when we look at the cardiovascular system, what we're talking about is your heart, your blood vessels and your blood. So that's what the cardiovascular system is made up of. It's all about transporting the blood around the body. So the heart's the one that actually pumps it, the blood vessels transport it, and obviously the blood is what we're looking at. It has three main functions. The first, really simple one, it transports oxygen and carbohydrates and nutrients around the body. So it's taking oxygen to the muscles or to the organs, taking carbon dioxide away. It helps the blood clots when we have those scabs to stop blood continually pouring out of us. That's the cardiovascular system that's responsible. And lastly, it also controls our our body temperature. So being able to cool ourselves down, being able to keep ourselves warm and keep hold of that heat is part of the cardiovascular system. So if we look at the first one, transporting oxygen and carbohydrates, we know the heart pumps oxygen around the body, which it it pumps oxygen around the body and then it releases energy stored as glucose in the cells. If muscles need to work for longer, so if we're doing exercise, we need to get more blood to those muscles because it needs a greater amount of oxygen. So when we're exercising, our heart pumps faster but also harder, so it releases more blood per beat as well as more blood per minute because it's pumping faster. We've then got it that it helps the blood clot. We will look at in a minute what his blood is made of. It's not just blood. Again, it's broken down into lots of different components. But it's the platelets inside the blood that helps the blood clot. So if we cut ourselves, the platelets will help to clot the blood. So it goes to the surface of the cut, wherever we've got that cut, and it will form a scab to stop it bleeding. We'll go into more of that, but obviously that's really important. Whether we're doing sport, whether we're doing anything, we need to be able to prevent our blood from spilling out of us and keeping hold of it. So the first two, a bit more, it does this and we just need to know it. This one we need to go into a bit more detail and be able to understand how it does it. So our cardiovascular system controls body temperature, and it's the blood vessels that help us to cool down when we're too hot or help us to keep hold of heat if we're cold. And it does this by these two terms, vasodilate and vasoconstrict. So what that means, vasodilate, imagine if we're talking about our arm and how we're going to lose heat for our arm. We've got lots of blood vessels going through our arm. We're really hot at the moment, so we want to get rid of heat. So what's going to happen is the blood vessels are going to vasodilate. They're going to get bigger. And when they get bigger, they go towards the surface of the skin. So you know when we're playing sport and you can see that we're really red? Because the blood vessels have gone close to the skin. Once they've got closer to the skin, we then lose heat through radiation. So if we're really hot, the blood vessels will vasodilate, which means get bigger, and they get closer to the surface of the skin, which we can see when we get red, and then we lose the heat through the process of radiation. What happens when we're cold and we want to keep hold of our heat?
Smaller.
Good, the blood vessels get smaller, they move away from the surface of the skin, and we lose less heat. So the terms that it's called for getting bigger and smaller, vasodilate, dilate means gets bigger. Have you heard the word dilate when we talk about our pupils, when your pupils dilate? And vasoconstrict, constrict means get smaller. Just ignore this slide for a second. Before we do that, I want to have a go. Say it in your head first. I'm going to give you 20 seconds. How do we lose, Jemima, you're going to do lose heat. Senan, you're going to do keep hold of heat. I want you to explain the process using the terms vasodilate and vasoconstrict. How we lose heat and keep hold of heat. Process it in your head first so you've got it. Do you reckon you got it? Your sports sorted, Connor?
The blood vessels get bigger and wider and go closer to the skin, so that
Which is called?
vasodilate.
Good.
And it makes it easier to let the heat out of the body and the skin.
And what's the process where we lose heat? Begins with R. Ray. Yeah, radiation. Senan, go for it. How do we keep hold of our heat? Because it's cold now.
So the blood cells get
Not blood cells.
blood
Begins with V. Blood. What carries?
vessels
Good. Blood
get
vessels.
smaller and go like more away from the skin.
Good. What's that called when they do that? They vasoconstrict.
Contract.
Vasoconstrict.
Constrict.
Good.
Yeah, and
And we lose less heat through.
radiation.
Perfect. Okay, so we've had a look at how we maintain body temperature and about the blood vessels, but we need to look at what blood vessels there are. So we've got arteries, veins, and capillaries. So I've used the colours. The arteries are generally oxygenated, they carry oxygen. Veins generally don't have any oxygen. Capillaries, join the two together, will have a bit of both. So arteries, how I best remember is A for away. Arteries carry blood away from the heart. So all arteries will always go away from the heart and take the blood away from the heart. Because they're taking blood away from the heart, if you imagine that heart pumping, it pumps really fast and strong. So the blood's going to be travelling at really high pressure because it's just forced it out, so it's going to be moving quickly. So because of that, the arteries need to be able to cope, so they've got thick walls. If they had really thin walls, the pressure of the blood would burst it. So we know that arteries carry blood away from the heart. The blood is pumped out, and therefore there's high blood pressure within the arteries. Because of that, we've got thick walls so they can cope with that pressure inside them. Does that make sense?
Yeah.
So because arteries are going away from the heart, the blood pressure is really high, and then the arteries have adapted to have thick walls to allow for that high blood pressure. Because of the blood pressure, if you imagine we've got a thin tube, the blood's travelling down, and it's going down fast, it's arteries that have the pulse, because as the blood travels down it, you'll feel the pulse in your, it'll be in certain places, but because of the pressure you can feel a pulse. You won't feel a pulse in the veins because they don't have that pressure. So when you're finding your pulse, that'll be an artery that you're feeling, not a vein. And lastly, the channel inside the artery, so our artery is like this, that bit inside is called the lumen. So it's like the space, the surface, not the surface area, it's like the capacity inside is called the lumen. So how wide it is, how big the diameter is inside that vessel is the lumen. And it's got a wide lumen that can widen and restrict to allow how much blood goes through. So arteries are able to vasodilate and vasoconstrict to control how much blood goes through them. If we look at veins, if arteries are going away from the heart, where are veins going?
Towards the heart.
Yeah. If they're going towards the heart, do they have high or low blood pressure?
Low. Because there's nothing like pushing it as well.
Yeah, the heart's done all the hard work, it's pushed, imagine my heart's here, it's pushed the blood all the way down to my feet. Now the veins have got to bring it all the way back up, so it's not got much pressure left at this point. So imagine the heart's pumping, every beat is beat, and the blood is pushed a bit further. And because the blood from here is being pushed, it's helping to push it back up as well. But in between every beat, in the veins, there's low pressure, so it starts to drop back down again. So imagine it's going beat, the blood goes up, in between the beat it falls a little bit and goes up. To stop it going backwards, because we don't want blood to go backwards, veins have got valves, which are doors. So if imagine the veins going up, and these are my doors here that open and close. When the heart beats, it pushes them open, so the blood goes up. In between the beats, they close. So it doesn't ever drop back down.
One-way door.
It is just a one-way door, so it lets blood through, but it doesn't let it go back again.
Yeah.
So they're called valves. So veins, have a low blood pressure, and because of low blood pressure, they've got these valves that open and close. So the blood will go up with the beat, in between it closes. Up with the beat, in between it closes. So we've got veins carry blood away from the heart, therefore they have a low blood pressure. To allow for that low blood pressure, but to keep the blood going in the right direction, I'm going to ask you a question on that in a minute, they've got valves. Tell me about the thickness of their walls if they're travelling at low pressure. Well, yeah, they're not as thick as the arteries, they don't need to have it, so they've got thinner walls. So we've got, as the blood travels around the body and is now travelling back to the heart, the blood pressure is much lower. This means they have a thinner wall and rarely pulsate. So rarely do you feel the veins pulsate. Due to low blood pressure, we also have valves, and valves prevent the backflow of blood and open and close of every heartbeat. We'll look at valves again in the heart because they're also present in the heart. But what we need to remember for valves is that they prevent the backflow of blood. So it prevents blood from flowing backwards. If you can remember that, that is the purpose of all valves, whether they're in our arteries, well, they're not in our arteries, whether they're in our veins or our heart, they always prevent the backflow. And what we've got now is our capillaries. So imagine we've got our heart, we've got arteries that are taking the blood away from our heart. They need to drop off the oxygen at wherever they're taking it to before they get to the veins. And it's the capillaries that are at the tissues that will allow for that. So we'll have arteries, capillaries, veins will take it away. So we've got our capillaries that will be half oxygenated and half deoxygenated, depending on where they are, because they're connected to the arteries. They've got oxygen to begin with. They then get rid of the oxygen at the muscle and then take it back to the veins. So in between, so half it will have oxygen and half won't. They're really small, they're just 1 cell thick. And that's because it needs to let oxygen through and carbon dioxide through. So imagine we've got blood at the heart. The oxygen in the blood is gone down the artery, and we've now got to our quadriceps, and we're going to give the oxygen to our quadriceps because we're running. So it goes to the capillaries, we get rid of the oxygen at the quadriceps, and we get the carbon dioxide that is there, and then we take it back in the veins. So to the heart that we can then take to the lungs and breathe out. So because we need the gases to pass through the wall, they need to be really thin, so they're literally just one cell thick. And that allows oxygen to pass through and carbon dioxide to pass through to come back. So it allows it to be efficient. So we've already looked at this, that they connect the arteries and veins. And that process of when we swap oxygen and carbon dioxide is called gaseous exchange. Have we heard of that before? You have. Fiddle? Don't worry if you haven't, because we're going to learn about it here. So the swapping of gases is called the gaseous exchange, which makes sense. We're exchanging gases. And we'll do that at lots of different places throughout the body.
Seems a bit odd though, doesn't it? Because you just pump the blood to get rid of it, to then bring it back up, to put it in again.
So if you think about the blood,
It's like
blood is just like the car. So we've got the blood vessels, which are the roads in our body, and the blood is the car that is literally just carrying the passengers, which is the oxygen, to create energy to then pick up the passengers that we don't like and get rid of. So think about the blood is literally, that's all it's for. Has no other purpose really. We mainly just want to supply oxygen. So this is what it looks like. Can you see the artery is quite thick here? The veins thinner, although it's not completely thin, and then we've got this really thin one here of the capillary. So we've got arteries go away, veins go towards, gaseous exchange happens at the capillaries. Are we happy with that?
Yeah.
Okay, you have got, let's label them 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 that way, so go down. I want you to work out what are they referring to, arteries, capillaries or veins. So have a quick look and then we'll go through them together. Okay, Jemima?
Arteries.
Arteries, good. Arteries have a pulse. Senan, very thin walls.
Capillaries.
Good. Have valves.
Veins.
Thick muscular walls.
Leather. Veins.
Which one has high pressure, so has to have thick walls?
The
A for away.
arteries.
Arteries, well done. Carry blood towards the heart.
Veins.
Veins. Elastic walls.
Capillaries.
The elastic walls, what it's referring to is they're able to stretch to allow the high pressure.
Oh, so the
Arteries, well done. Carry blood at low pressure.
Veins.
Carry blood away from the heart.
vein? No, arteries.
Good, A for away. Carry blood at high pressure.
Arteries.
Very narrow, one blood cell at a time. One blood cell at a time.
Capillaries.
Capillaries, well done.
Yeah.
So we've got capillaries in purple, veins in blue, and arteries in red. Okay, blood distribution. So when it's discussion, it's a really small discussion between just the two of you. I'm going to give you just 1 minute to talk to each other. When and why would the arteries need to change size to direct the blood flow? So I've not taught you this. This is can you work out. So think about what we've talked about, how they vasodilate and vasoconstrict. So they can affect the blood distribution. But why would arteries ever need to try and choose where blood goes? Don't tell me, tell each other. I'll stop listening.
Certain parts of the body need more blood than other parts.
Yeah, maybe if we're doing certain sport that might need more blood than like another part.
Like if you're doing handstands, your body has to try and stop sending the blood to the head.
Or
Anything else? You've got the gist of it. So when we're exercising, it's our muscles that are working, so they need the blood, don't they?
yeah.
When we're eating, our digestive system is working, that needs the blood. So we need to choose.
Whatever your body's focused on doing, it needs the most blood.
Yeah, and our body's really clever. It's not just going to equal out the blood and keep it the same amount of oxygen regardless of what we're doing. If you're going to go run a marathon, you need a lot more oxygen then than you sitting here now. So your body needs to adapt to that, and your body will. So we've talked about vasodilation and vasoconstriction for body temperature, but now it's going to be exactly the same when it directs blood flow. If I am doing squats and my quadriceps are working really hard, so it needs more blood, how will the arteries allow them to get more blood, do you think? So that's all right. So imagine it, my quadriceps are working, so they are going to need more blood flow there because they need more oxygen to work. How can the arteries help them get more oxygen?
Pump more blood to that area and make it bigger so it stores it for longer so that there's more access to it.
Right, say that again for me. I have to think about what you said. So the heart's going to pump more.
Heart's going to pump more to that area, then the veins are going to get a bit bigger so it can store it so that there's quicker access to it.
Is it the veins that's going to... You're getting there, good. So the arteries that are going to the quadriceps are going to get bigger. What's that called? Dilate. Good. So the arteries that are going to our quadriceps are going to vasodilate and get bigger, which means more blood can go through and then they get a higher concentration of blood. If I am working this muscle and now my arms are literally just going to stand by my side and do nothing, what's going to happen to the arteries that go into my arms?
And then they're going to vasoconstrict.
Good. So that's going to reduce the blood flow there and allow more to go to where we want it to go. So that process of vasoconstriction and vasodilation allows us to choose where we want the blood to go. So it's involuntary. You personally don't say, come on blood, I wouldn't need you here now because this is getting tired. It will do it by itself, but your body will work out where it needs more. So I've said that exercise causes the distribution of blood in your body to change. So as soon as we start exercising, the distribution changes. Muscles need a lot more blood for movement, and so your body works to get more blood to the muscles. This is called vascular shunting. So that's something that has come up in exams before. The term vascular shunting, it might ask you to define the key term or ask what it's referring to. And it's referring just to the blood distribution, so choosing where the blood needs to go is vascular shunting. So areas such as the digestive system need less blood during exercise. We don't need our body to be digesting food during exercise. Our bodies focus on creating energy for exercise. Therefore, blood flow is restricted via vasoconstriction to increase the blood flow to the working muscles. The more you exercise, the more efficient your body becomes. So we know this, really. The first time you go for a run, it's quite tough. We can't seem to create enough oxygen to be able to give us enough energy to run far. The more we train,
used to it.
yeah, and our body adapts. It won't just be this that makes us better at running the more we do, but this is part of it. So our body will adapt in lots of different ways, and we'll look at the long-term adaptations soon. But this is one of them. The vascular shunting and blood distribution, our body can do it, but the more we have to do exercise, or the more we do exercise, the better our body becomes at getting more oxygen to those muscles that need it. And then afterwards, when we think about warming up, allows our body to start the process. So we never just go into exercise before we warm up. The warming up gets this bit started. By the time that we are doing our main event, we're getting more blood to those working muscles and we're more efficient at creating energy, and also injury and everything else that we need to look at. And again, the cool down allows your body to gradually return. We don't just want to stop exercise straight away, because then our blood doesn't gradually start returning to how we need it to normal. It needs to make sure that we do have that gradual change.
Can't like if you don't do that, can't that also affect how like effective it is? Like not so much the actual working out, but like how well you. So like if you don't do the cool down, the next time you do it, your body won't have adapted as well.
Yeah, the cool down will help your recovery process.
Yeah.
So if you start to cool down and stretch afterwards, you shouldn't have so much ache after. You'll still have some depending on how hard you've worked, but it will allow quicker recovery. It's also really dangerous for your heart rate just to all of a sudden drop massively. We need to gradually look at our heart rate. There'll be a big section on warm-ups and cool-downs that we'll go into, but that's completely right. So far, what have we looked at today? We have looked at types of blood vessels. If we look at just the cardiovascular system, types of blood vessels and how those blood vessels work. So now we're going to look at the actual blood that's inside it. Do either of you know there's 4 components of blood? What are they? What's in your blood? What have you got? What's blood made up of? Blood cells. There's 2 types of blood cells.
White and red.
Good. We've got red blood cells and white blood cells. I've spoke about one earlier that helps form clots. Yeah, what forms it? That's what I'm referring to. Begins with P. Think about what do you eat your dinner off? Platelets. So we've got red blood cells, white blood cells, platelets, and there's one more that begins with P. You might not know it. It's more of like the water as such within the blood. Plasma, have you heard of that
Oh
before?
yeah, I was doing that in biology.
Oh, so you have heard of this. So if we look at the red blood cells, they're also known as erythrocytes. I don't know if I've actually said that right. Generally in exam, I don't think that will so much come up. You'll be allowed to call them red blood cells. But it's part of the specification, so we need to be aware of it. But you won't lose marks for calling them red blood cells. That's absolutely fine. They've got a pigment. The red blood cells are red. And it's the hemoglobin in the red blood cells that gives them that red colour. Have you heard of hemoglobin before? No? Okay, all the hemoglobin is what the oxygen, what carries oxygen. So it's the hemoglobin in the red blood cells that carries the oxygen to wherever it needs to go. So here we've just said it here. Hemoglobin attracts oxygen and carries it to the tissues. Just in this last little bit here, a low red blood cell count, which is when we're anemic, so if you've got not as much red blood cells, causes you to be breathless and lack an energy. So if we think about in terms of exercise, having a low red blood cell count is not going to be beneficial for exercise. We don't want to be breathless and we don't want to lack energy. Like the two complete opposites of what we want when we're exercising. And then just in terms of a bit more knowledge, to increase the red blood cell count, we need to increase our iron intake, and that will allow us to increase it. And if you know anyone that's anemic or have heard of that before, you might have heard of that about iron. So now we've got opposites. So we've got our red blood cells, which their job is to carry the oxygen. It's the hemoglobin inside it that carries the oxygen. And our white blood cells, and their job is to fight off illness. So their job is being our immune system. So they're the defence system of the body, and they destroy pathogens which cause illness. They destroy the pathogens with chemicals called antibodies. So it's the antibodies that the white blood cells create that will allow us to kill off the pathogens. So we've got red blood cells, carry the oxygen. We've got white blood cells, which are our immune system, they fight off illness. And our platelets, which we've already looked at, which allow the blood to clot. So really important to carry the oxygen to the tissues, really important to stop us being ill, and lastly, really important to stop that blood, or to allow that blood to clot when we have a wound. These platelets are formed in the blood marrow, and they're vital in the clotting of blood. So when we cut ourselves, the platelets come to the surface of the skin, and they swell, so they get bigger, and they create like a sticky substance that clots and allows it to stops it from bleeding. So they act like a plug. So imagine it's just an open cut, and it's those platelets that act as a plug to stop that blood from leaving. And then over time they harden, obviously form a scab.
Unless you're us. We have a blood clotting disorder.
Unless you can't. That will help you to remember it though. What's the last one called? Think about TVs.
Plasma.
I don't know. Makes me think of TVs anyway. So plasma is made up of 90% water, so it is almost all water, and it contains plasma proteins, and it's those plasma proteins that are important for maintaining circulation between the cells and tissues. So we need the blood to be fluid. It needs to travel through the arteries, the veins, and all of the vessels. So we need to make sure that we have this, and without this plasma, oxygen transportation cannot happen. So this plasma is vital in allowing oxygen transportation. What are the 4 types of blood?
Voluntary. Oh no.
Sorry, not
White
4
blood
types of blood,
cells.
4 components of the blood, sorry.
Platelets, white blood
Platelets,
cells,
white blood cells,
red blood cells.
Plasma.
plasma, well done. Red blood cells, what's so important about them? What's inside the red blood cells begins with H that carries a really important gas. What's the gas that's really important that we need to take to the oxygen? And it's the hemoglobin that carries the oxygen. So that's the importance of red blood cells. What's the importance of white blood cells?
They fight diseases and infections.
Good, they fight diseases and infections.
The
Platelets.
platelets. They form blood clots and scabs.
Good. forming the blood clots and scabs to stop us from losing blood. And plasma,
They
what's it made up of?
90% water.
And it's vital in oxygen, begins with T,
Oh,
tram, sport.
taste.
Yeah. So the plasma is 90% water and it's vital for oxygen transportation. So now we've looked at how the blood travels around the body, what the blood's made up of, what the vessels are like that carry that. So we need to look at the heart. Do we know anything about the heart in terms of chambers, in terms of valves, in terms of anything?
It pumps blood.
Perfect, it pumps blood. So it's really, really important. What type of muscle is the heart? Cardiac muscle. So it's an involuntary muscle, but it has its own specific type. It's cardiac muscle. So we're going to look at all the different sides of it. So you should have, so then that one's there, yours. Your heart that you're able to label as we go. So the top two chambers are the atriums. When you look at the heart, you need to imagine that heart's inside you. So you're not looking at it to look face on, because if you was looking face on, this would be your left side and this would be your right. But this heart is now inside my body. So this side is my right side and this side is my left side. Does that make sense?
So the opposite.
So it's the opposite.
Like when you're on a stage.
Yeah. Yeah, like the right and left hand side of the stage, because you imagine it when you're on it, not to look at.
Yeah.
So we've got the top two chambers. The heart's divided into 4 chambers. We've got this one, and these chambers down here. So the top 2 are called the atriums. We've got the right atrium and the left atrium. And then next, we've got the bottom chambers, and these are called ventricles. So again, we have the right ventricle and the left ventricle. So atriums at the top, ventricles at the bottom. A comes before phi, so A is always first. So they're the 4 chambers of the heart. Also inside the heart we've got 4 valves. We've got a valve here separating the 2 chambers on each side. So we've got one valve that separates the right atrium and the right ventricle. We've got another valve that separates the left atrium and the left ventricle. And then we've got 2 valves, one here and one here, when the blood leaves the heart. So the blood leaves the heart twice. First time it leaves the heart to go to the lungs to collect oxygen, then it comes back to the heart, and then it leaves the heart to go to the rest of the body. So when we look at these valves, our first 2 are the ones that separate the chambers. This is called the tricuspid valve and the bicuspid valve. The way I remember this is you try before you bi. So both got cuspid, but we try on the right hand side and we bi on the left. So the tricuspid valve separates the 2 right chambers, and the bicuspid valve separates the 2 left chambers.
Yeah, I thought it didn't go around.
So you always try before you bi. You don't bi before trying. And the next 2 valves are more linked to the artery that they're connected to.
Yeah.
Sure. So these ones here are the pulmonary valve, which separates the right ventricle and the pulmonary artery. And then we've got the aortic valve, which separates the left ventricle and aorta, which is this main artery here. It's hard because you can't really see this valve, so I've done a circle, but it's in that blood vessel.
Which arrow is it on?
It is.
Because there was one exactly to that area.
I think it's this one here.
It goes to this bit here.
Okay.
Can you see that arrow?
Yeah.
Thank you.
Sorry.
Oh, I didn't know that.
That's why I just crossed it out. It's not the end of the world. Let me have a look. So that one's the aortic valve, and then this one here, so the one above is a bicuspid.
That one.
So that's bicuspid, and this one's aortic. So the tricuspid and bicuspid separate the different chambers, and the pulmonary and aortic are linked to the artery that they're connecting to. So we now should be able to label the 4 chambers and the 4 valves. We need to look at the vessels that come into it and go out of it though. So, this big one here, this is the main vein in the body. It's called the vena cava. We've got the superior vena cava, which comes to the top of the heart, and the inferior vena cava that comes from the bottom of the heart. So this is our main vein of the body. The vena cava is the vein that will bring the blood back to the heart. If it's bringing blood back to the heart, is it going to be oxygenated or deoxygenated? Yeah, because it's already gone to the muscles, it's got rid of all the oxygen, and it's come back. So we've got the superior at the top, inferior at the bottom. We've then got the main artery of the body, the aorta. So the vena cava is the main vein that brings blood back to the heart. The aorta is the artery which it leaves the heart to travel to the rest of the body. And that's that round bit here. Can we see that the colours represent oxygenated and deoxygenated? So the vena cava is the main vein in the body, the aorta is the main artery. Then we've got these two here that will carry blood to the lungs and then back to the heart again. Because they're going to the lungs, they're called pulmonary. One's the pulmonary artery and one's the pulmonary vein. Which one's the artery, the blue or the red, and which one's the vein?
The veins blue.
The vein's blue and the artery's red?
Yeah.
That should be right, shouldn't it? Because veins are always deoxygenated, arteries are always oxygenated. This is your one exception. If we think about it, it makes sense. So the blood's gone to the muscles, it's got rid of oxygen, it's now deoxygenated. And it's going to come back through the vena cava into the heart. Still deoxygenated, yeah? Has it gone to the lungs yet?
No.
No, so it's not going to have oxygen until we've collected it from the lungs. But because it's going away from, because the artery's going away from the heart, without oxygen to get the oxygen, that's the one artery in the body that's deoxygenated. Because the blood inside our heart has already got rid of the oxygen at the muscles, and it's now inside our heart being ready to pump to our lungs, and the pulmonary artery is taking it to the lungs. Then on the way back, it's now got the oxygen, it's gone from the lungs back into the heart through the vein, but this is the vein here, but it's now oxygenated. So this is the only one where it's the other way round. So the pulmonary artery is this one here, which is taking the blood to the lungs, and the pulmonary vein are these ones here, going back into the atrium. So that is the only artery and vein that carry the opposite. Apart from that, arteries will carry oxygenated blood and veins will carry deoxygenated. We've got two more things to label on the heart. I think you should have 2 arrows left. Okay, last two are just these bits here. So the wall of the inside of the heart that separates the 2 ventricles is called the septum. And this bit here is called the chordotendae. So it can refer to it maybe as the heartstrings. It's just the muscle that connects the tricuspid valve here. And they're like cords, so it's these stringy bits here that we're referring to that's attaching in the valve to the heart. Can you see it on
I
there?
think I labelled the wrong one.
Which one do you think's wrong? Have I not done enough? No, I don't think I've done enough arrows for you. Just your own arrow here.
Okay.
Because it's the inferior vena cava I haven't done an arrow for. Sorry, so on your sheet, I've just noticed there's not an arrow going to the inferior vena cava.
Oh yeah, I drew one.
Did you draw one? So then yours should be fine with the arrows, perfect. So what we're going to look at, so we've labelled it all. We're now with your sheet so you can see it all. We're going to look at the pathway of the blood through the heart and be able to talk about it. So this is our sheet, so yours should look like this, although you'll be able to see your writing. Mine's gone the wrong way around. Let's talk about how the blood goes in the heart, travels around and goes out. So, the blood goes in. I'm going to do it the first time and then I'm going to let you two try, but you've got all your labels there. The blood goes in via the superior and inferior vena cava. It enters the right atrium and passes through the tricuspid valve into the right ventricle. It then passes through the pulmonary valve into the pulmonary artery to go to the lungs to collect oxygen. It comes back in the pulmonary veins into the left atrium, through the bicuspid valve into the left ventricle, through the aortic valve and through the aorta to go to the rest of the body to deposit oxygen at wherever it's needed. Easy?
Yeah.
Do you want to do it, or do you want me to say one more time and then you try it?
I'll do it.
Go on then, you go first.
It goes in the superior and inferior vena cavas
Perfect.
into the right atrium. Then it goes through the
Tricuspid.
tricuspid valve into the right ventricle. Then it goes out the pulmonary valve and through the pulmonary artery to the lungs to collect
To collect what?
to the lungs to collect oxygen.
Yeah.
Then it comes back in the pulmonary vein.
Yeah.
And then into the left atrium, down the bicuspid valve into the left ventricle, and then out of the
Aortic.
aortic, and out of the aorta
Perfect.
to the rest of the body.
You ready, Senna?
Yeah.
Do you want me to do this, or do you want to just go for it without me? Am I in the way when I'm doing that?
I can try.
Go on then.
It goes in through the superior vena cava and inferior vena cava.
Vena cava, perfect.
Then into the right atrium,
Yeah, through.
the tricuspid valve,
Perfect.
and then
What's it gone into after the tricuspid valve? What's this chamber here at the bottom? This is the right atrium, this is the right ventricle. Perfect.
and then up to the
We've done a tricuspid.
pulmonary valve, and
Good.
then up. That is
It leaves the heart through the.
pulmonary artery.
Good. Where's it gone to?
Get oxygen from the lungs.
Perfect. How's it going to get back to the heart
Through
through the?
the pulmonary veins.
Perfect. Into the.
The left atrium.
Through the.
What is it? Bicuspid.
Valve. Perfect. Into the.
The left ventricle, and then
Through the aortic
valve.
and out of the heart through the
Aorta.
aorta. Perfect. Okay. Fill in the blanks. Blood flows into the heart via the something and something.
Superior vena cava and inferior vena cava.
Perfect. Through the superior and inferior vena cava. Blood enters into the
Right atrium.
right atrium of the heart. Blood flows through the something valve,
Pulmonary.
not pulmonary,
Tricuspid.
tricuspid valve. Pulmonary is the one that's attached to the artery. Through the tricuspid valve into the.
Right ventricle.
Good, so we've gone from the right atrium through the tricuspid valve, we're now in the right ventricle. Blood flows out of the. What arteries are going to flow out of the heart to the lungs to?
Pulmonary valve.
Not.
Veins.
Oh, sorry, this is the way it's worded, so you're right, but it's just worded different. Blood flows out of the pulmonary artery, because it's going away from the heart,
Oh.
through the pulmonary valve, and into the. Where's it gone to? Pulmonary is referring to the lungs. So we've now out of the heart and we're at the lungs.
Oh.
Blood flows to the lungs to collect oxygen through the process of gaseous exchange. So all that's referring to is the swapping of the two gases. Blood flows back into the heart via the pulmonary veins, good. And blood flows into the left atrium through the something valve. So it's gone
Oh, the
by
bicuspid.
bicuspid valve into the, what chamber's at the bottom now? You lost where we are.
Left.
No, I got confused. Sorry.
So we've gone from the left atrium through the bicuspid valve and now we're in the left.
Oh, I didn't realise you went past the blank because I just heard you say blood flows into the left atrium.
Oh, okay, no, that's fine.
So
That's right. And now where are we? What chamber are we in now?
The left ventricle.
The left ventricle. Blood flows through the something valve, aortic valve, to enter into the aorta to leave the heart. Happy?
Yeah.
We're going to go over and over and over it until it just sticks. So, I'm going to be nice. I've given you all of the codes. I'm going to give you 2 minutes. Just keep on repeating. So look through here. Look at the codes. They stand for the initials of whatever it is. The vena cava. Obviously, you know superior and inferior. And I've given you all the arrows that will tell you exactly where it goes. 2 minutes to revise it. Then I'm going to take all the labels away, turn your sheets over and ask you to do it.
I remember doing a key stage 1 experiment with zipper bags and straws. I have to bring that every time again.
Hey Jemima, voice it out loud. I'll let you keep those on for the first time.
They go in through the inferior and superior vena cava
Good.
into the right atrium, then through the tricuspid valve into the right ventricle, then they go through the pulmonary valve out of the pulmonary artery into the lungs, and then they come back into the heart through the pulmonary vein. They come to the left atrium, through the bicuspid valve into the left ventricle, through the aortic valve? Is it a valve?
Yes.
Aortic valve, and then out of the heart through the aorta.
Perfect. Go on then, Senan.
They go in through the superior and inferior ventricle,
Vena cava.
vena cava, then into the right atrium, then to the
Think of the valves as doors. They go through the valves. They go through the
tricuspid valve,
Good.
and then into the right vena cava,
Is that the vena cava? What the
No.
chamber's called? The right
then
Cool.
ventricle,
Good.
then up through the pulmonary valve,
Good. It's gone through the pulmonary valve into the
pulmonary arteries
Good.
to collect lungs and exchange gases.
To collect the lungs. To go to the lungs.
To the lungs to collect.
Perfect.
And then it goes back into the heart through the pulmonary vessels.
It's definitely a vessel, but what type of vessel? Is it artery or vein?
Artery, no vein.
Good, yeah, it's gone back to the heart through the vein. So the pulmonary vein into the... Where are we now? We're at the...
Left atrium,
Good, through the...
bicuspid valve,
Good, into
to
the...
left
Then...
ventricle,
Good, through the...
aortic valve,
Good, and out of the heart through the...
blood through the
Aorta.
aorta.
Aorta. Don't worry, it's the first time you're going through it. Jemima.
They go into the inferior and superior vena cava,
Good.
into the right atrium, through the tricuspid valve, into the right ventricle, through the pulmonary valve, into the pulmonary arteries that goes out the heart to the lungs, and it comes back through the pulmonary veins, into the left atrium, through the bicuspid valve, into the left ventricle, through the aortic valve, out of the heart through the aorta.
Perfect. You ready, Senna?
Yeah.
Jemima, I'm not going to say anything. If Senna needs any help, you're going to help.
Okay.
Okay, so it comes in.
Through the superior and inferior cuspid
Vena.
vena. I can't remember.
Go on.
Vena cava.
Vena cava.
Then into the right artery. No.
There's lots of A's and everything. Eight.
Atrium.
Good.
And then like through the bicuspid.
Okay, but
What do you
try-
do before you buy?
Sorry.
What do you do before you buy?
Tricuspid.
Good. So we've gone from the right atrium through the tricuspid valve.
Into the right
The
ventricle.
yeah.
Then up through this pulmonary
That's your doors there, isn't it? Pulmonary what?
valve. Then out through the pulmonary artery. To go get oxygen from the lungs. Then comes back through the pulmonary vessel. Not vessel. The veins. And then into the left atrium. And down through the right.
We have to go through something.
Oh, the
Is-
tri.
We tried over here. We're now going to
Cuspid.
perfect bicuspid valve into the
Right, the left, ventricle,
ventricle. Well done.
and then up into the aortic valve.
Aortic valve out the aorta. Perfect. That's quite tough to learn in one lesson. A lot of people learn it, go away and go over and over, so don't stress. Okay, key terms referring to blood flow. So when we're talking about the beat of the heart, we need to understand these two key terms. The stroke volume is the amount of blood the heart pumps per beat. So every time it beats, the stroke volume is the amount of blood it pumps out. Whereas the cardiac output is the amount of blood pumped per minute. So however much blood you manage to get around the body per minute is your cardiac output. So thinking about how those two relate, our heart rate, so the number of times our heart beats per minute, times by how much blood per beat is our cardiac output. Does that make sense? So think of every beat the heart pumps a certain amount. If we times it by how many times it beats per minute, we get how much blood is pumped in a minute.
Yeah.
Okay, just on the back of your paper, if you need to write down any notes, just write it on here or there. That's because I haven't written the question down. Oh, sorry. So just in case you need to remember it. Michael's heart rate is 77 beats per minute. And this is not accurate, but his stroke volume is 50 millilitres of blood. What is his cardiac output?
Can you say that again?
Yeah, his heart rate is 77 beats per minute. His stroke volume is 50 millilitres of blood. What's his cardiac output? And that 50 millilitres is not accurate, I've just made that up.
What's his stroke volume?
It's 50.
Sorry.
That's right. What's his cardiac output? How are we working it out? What are we doing? So I've given you his heart rate and I've given you his stroke volume and I want his cardiac output.
7 pumps 50.
Yeah.
Times or plus?
Times. So if you think about it, it's the amount it pumps per beat and we want to know how much across the minute. So it's going to pump 77 times. So we need to times it by 77 to work out what his cardiac output is. So that 77 isn't referring to an amount of blood, it's just referring to the amount of beats.
Is there a certain way you need to like? This is maths.
It's just maths.
I'm not good at wait.
But you'll need to remember this.
Can you time stuff like either way around?
So you can times 77 by 5 and add a 0.
Might have done it wrong actually. I think I did the maths wrong. Yeah. Okay.
Times it by 5, just add a 0. So when you do 77
Oh, I remember that.
times by 5. So 5 times by 7 is
35.
25.
Okay.
You did, and then you added some 7.
Yeah.
What's his cardiac output?
So what do I do wrong? I'm confused still.
This one's right. So you
Oh.
added an extra 77 on for some reason.
Oh, yeah, 3,800.
3,850.
Also, I know that.
It's fine, it's just to be able to understand. You need to, the exam question might ask you to define them.
I don't know why I added 77.
No, I'm not sure why you did that. Your mind went just blank for a minute. So you need to be able to define these two terms. Sometimes a question will ask you what's the relationship between them. If it's asking the relationship, it wants the formula. If it's asking a question about these at all, you can write the formula like that. It doesn't need to be written out. I'd probably maybe write a heart rate, stroke volume, cardiac output, but you can do this rather than trying to explain it in words. You don't need to say heart rate, the number of times your heart beats per minute times by stroke volume will equal your cardiac output. You can just write this to get your mark. Ignore this bit. What is stroke volume, Jemima?
You don't have the volume
The volume of blood
per beat.
per beat. Cardiac output?
That was the amount of times it beats in a minute, or was that?
Not number of times, because that's our heartbeat. The amount of
Liters?
blood pumped out per minute. What are the top two chambers of the heart called? The top two.
The left and right atrium.
Atriums. What are the bottom two called?
Left and right,
Ventricle.
ventricle.
What are the valves called that separate the chambers?
The tricuspid valve and the bicuspid valve.
Good. What are the valves called that attach to the arteries that leave the heart?
The pulmonary arteries and.
Careful, because I'm asking you about the valves. So the
Oh,
pulmonary valve and the
pulmonary aortic valve.
valve. Jemima, what's the wall down the centre of the heart called?
That was the one in your nose.
Sep. Think of 7 in French.
I don't know, friend. Wait,
Sep.
undos quest. Undos.
Ignore that, it'll take ages. Septum.
Sorry.
That's alright. Give me 2 characteristics of arteries. So 2 things that describe arteries. What do they look like? What do they have?
They have. They're bigger than the smaller ones.
Because they've got thick walls.
Walls and
What do they generally carry?
blood.
Blood at high or low blood pressure?
High.
High. Veins.
Carried oxygen with blood at low blood pressure.
Good. So they carry deoxygenated blood at low blood pressure, which is the one vein that doesn't carry deoxygenated blood.
Pulmonary artery.
Vein. Yeah, but pulmonary. Good. Okay. So we now can look at the heart, how the blood travels through the heart, the vessels that carry the blood, what's inside the blood, but now we need to understand how the heart actually works. So we know the heart beats, but it's not just as easy as it beats. There's 2 phases, and we need to just understand those. So when we hear the heart contracting, they describe it as lub-dub. So you know when you hear your pulse or your heart beating with the stethoscope, you hear the lub-dub, 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 don't you? So you hear it twice. You don't just hear beat, 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 beat. You can hear 2 parts of that beat. Do you know what I'm talking about?
Yeah.
It's like da-da, 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 da-da. So each beat has got that 2 phases. And the phase is called the systole and the diastole. So one of them is when it's contracting and one is when it's relaxing. So phase 1 is the systole, and it's when the heart contracts. Phase 2 is the diastole, the heart's relaxing. So if we look at the systole, contraction happens in 2 waves. So it's why we hear that duh-duh sound, because it happens in 2 waves. So wave 1, blood is pumped from both atria to the ventricles. So blood's gone from the atrium to the ventricle on both sides. So that happens in phase 1. Phase 2, or wave 2, sorry, the ventricles contract and the blood is pumped to the lungs or the rest of the body. So both sides of the heart work symmetrically. So we're in the systole, so which is referring to the heart contracting, so the heart's working. Wave 1, blood is in the atrium, the right atrium and the left atrium. So wave 1, it's pushed down to the ventricles. Wave 2, it's pushed out of the heart. So wave 1, down, wave 2, out. And then phase 2 is just the relaxing phase. The heart needs to relax to fill up back up with blood again. So when it's working, it's contracting, the muscles are working, and it's going to pump down before it goes out, because the blood has to leave the ventricles and not the atrium. So it has to go down and out. Phase 2, the heart just relaxes and it fills back with blood again. So then we can go back to wave 1, which is the blood going from the atrium to ventricles. Wave 2, which is the blood going out of the arteries. Does that make sense?
Mm-hmm. Yeah.
Which phase of the heart is it contracting? Systole or diastole?
Systole.
So which one's it's relaxing? Good. In the systole, the muscles of the heart contracting in 2 waves. What are the 2 waves?
Wave 1, wave 2.
Good. Perfect. That is right. What happens in wave 1 though?
Wave 1 was the bit where it was like... Can't remember the exact...
It's got to go down before it can go out.
Oh, yeah.
So the blood's got to go down
And
before it goes out. So what's wave 1?
the blood has to go down before it goes out.
Good. So the wave 1 is going down. Where's it going down from? Where from and where to? So it enters the heart on both sides into the left and right atrium. Good. So wave 1, it needs to go down. So where's it going from? The atrium to the ventricle, and then wave 2 is going from the ventricle.
Through all of the valvy things. And
Yeah, out of both arteries. It either going to the lungs or to the whole body. If it's going to the lungs, what artery is it travelling through to get to the lungs?
Pulmonary artery.
If it's going to the rest of the body, it's going to travel through the...
Aortic.
Perfect. Okay, this is a bit morbid and it might not help you, but this is how I remember things, and I think sometimes you need to have little tips to help you remember. So diastole, I think of the word die at the beginning. If you're dead, you're relaxed. So it helps me to remember die, the heart's relaxed and it fills with blood, whereas the systole is when it's working. So diastole, it's not actually doing anything, it's just relaxed to allow it to fill with blood. Okay, key terms. In all of these, we're missing, or the key term is missing, I've given you the description. Blood vessel carrying blood away from the heart.
Artery.
Good, A for away, artery. Blood vessel carrying blood towards the heart.
Veins.
Very thin blood vessels allow gaseous exchange to happen. Capillaries, well done. The chamber that blood first flows through when entering the heart.
Atrium.
Good. Prevents blood from flowing backwards.
So
The valves.
The artery that carries the oxygenated blood.
The pulmonary artery.
Perfect. Oh, sorry. This was arteries, but it doesn't necessarily have to be the aorta because it could be the pulmonary artery. Okay, questions. Can you write these down and do them alone this time to check your understanding? They're really short questions. Just realised question 5 I've not actually taught you. It's in the next lesson. There's a little picture, see if you can work
Is
it out.
supposed to be, just checking on it, question 2, is it supposed to be oxygenated or is it supposed to be deoxygenated?
Oxygenated.
Sorry, I'm getting confused. Sorry.
Does it make sense when I said that?
oh, okay.
Yeah, it was very chance discovery. We discovered that we're missing cotton factor 12. So we're not quite a haemophilia, but we're the next level down.
Sometimes it really helps to understand it when you've got to.
Yeah. It's quite interesting that it's actually completely irrelevant in the overall scheme of things, but we have to know we have it. No, we know, but it's
Well, do you
never
all
going
have
to
it?
Again, I got the most information out of the Canadian Health Service, but it's all about the cascade of enzymes, where we sit in that cascade, and the fact that I suffered terribly with nosebleeds, just random nosebleeds as a child. Simon's mum did. Nobody else did, he doesn't, so he must be the carrier, and I must have the active gene, but together, you both parents, to give the child, must have one must have an active gene, but you can be an active and a carrier, but then the children
It goes
will both
feeds
be
through.
active. Yeah. So,
Very low chance of having it.
yeah.
These are really quick, they're just like one word answers, you're not having to write much. On question 5, have a look at this picture to give you a clue. Don't worry about spelling. Which one are you on? Where's the pulmonary artery sit blood? Question 4.
Yeah. Oh, I know that. I was thinking of the wrong.
Yeah. So where does that come from? Where does pulmonary artery start and where does it go to? So arteries, remember A for away. So it's taking it from somewhere
From the heart,
to the pulmonary stands for
lungs.
So what are the role of valves in the heart? What do valves do in the heart?
Oh, they stop the backflow of blood.
Perfect. Which vein carries oxygenated blood and why?
The pulmonary vein.
Good. Why is that carrying oxygenated?
Blood.
So that you can bring it to the heart.
Because it can take it to the where, sorry? It's already at the heart. Sorry, no. Yeah, bring it to the heart from the lungs, sorry. What artery carries blood away from the heart to the working muscles?
Aorta.
Aorta. Where does blood from the pulmonary artery take blood from and to?
Lungs.
Good. Last one. So pulmonary artery and pulmonary vein, so it's going to the lungs, back to the heart. What links them?
The lungs.
So it is the lungs that link them. And more specifically, they're going to go to the alveoli in the lungs. And that's what we're going to look at when we look at respiration. But inside the lungs is alveoli, and that's where the gaseous exchange takes place. What is gaseous exchange?
Oh, gaseous exchange is where they swap they get oxygen.
The oxygen and the carbon dioxide.
Good, yeah, it's the exchange of oxygen and carbon dioxide. Okay, what's this?
Artery. Can't do it.
That one's a faint
Oh.
clue because I can see something here.
Oh yeah.
I don't know if you can see it.
Yeah.
And then this one is the
Capillary.
capillary. So we need to remember characteristics which define each. Who's going to do the artery?
I can do it.
Go on then, what's define? Well, tell me the characteristics that define the artery.
It's big.
It's got a what big begins with L. Do you remember that word? Do you remember when I talked about like the diameter inside? Lumen.
Yeah.
So it can change the size of its lumen.
I thought it was human.
No, L. Lumen.
Oh.
Sorry, keep going, Fenton.
So, and it takes the blood away from the heart.
Good. Takes blood away from the heart.
It has like a quick blood flow, sort of high pressure.
Good. Blood flows through the arteries at high blood pressure. And because of that, what's it got?
So it's got thick walls.
Thick walls. Perfect. It can also sometimes have a
Pulse.
pulse. Good. Perfect. Veins.
They have thinner walls than the artery. They have valves within them. They flow at low blood pressure, and they're usually blue or purple.
Yeah, and they sometimes pulsate, very rarely. Last one, capillaries. Tell me about the capillaries. How many cells thick?
They're very thin.
Very thin, only one cell thick.
They do the oxygen and carbon dioxide transfer.
Good, so they allow for gaseous exchange. Where do they meet? Where are capillaries?
The end.
Yeah, in between the arteries and the veins.
Yeah.
So they're at the tissue. So wherever gaseous exchange needs to take place, there'll be capillaries at the muscles to allow that exchange. There'll be capillaries at the lungs to allow that exchange. Good, so they carry blood away from the heart. They're elastic, which allows them to change size. They carry blood at high pressure. They've got a pulse. They've got thick muscular walls. And remember, they can change in size to moderate blood flow. That's the only thing that we didn't talk about. They carry blood, veins carry blood back to the heart. They've got thinner walls. They carry blood at low pressure, no pulse, and have valves. Capillaries have very thin walls. Gas exchange takes place here, and they link the arteries to the veins. Questions. Name the type of blood vessel that normally carries oxygenated blood.
Artery.
Good. Explain why veins need valves to fulfill their
So
function.
the back flow doesn't go like
Because,
this.
yeah, they have low blood pressure, so, and in between pumps, they would lose a lot of blood flow quickly if they didn't have
Yeah,
valves
yeah,
to
it wouldn't
keep
be
the
able to get
blood
up there.
up there.
Yeah, it hasn't got enough force, enough pressure to travel upwards, so it needs to
Keep
kind
it
of
in the
help
same
it,
place.
yeah, in between each one. Explain how one characteristic of a capillary makes it suitable for its function. What's the function of capillaries?
Gas exchange.
So tell me one characteristic that makes the capillary suitable for gases exchange.
Really, really thin ones.
Yeah, one cell thick walls, so it allows for gases to pass through. Arteries would not be suitable, they've got thick muscular walls, so gases can't get through them. Explain how one characteristic of an artery makes it suitable for its function.
Because it doesn't explode.
Because it has
So
thick walls.
what's the characteristic you're
It
talking
has
about?
thick walls, so
Good, to cope with the
high pressure.
high blood pressure, well done. Using examples, describe what is meant by redistribution of blood flow. That's tougher. So it wants an example. So we're doing PE, so it'll want a sporting example. So why do we need to redistribute blood flow during sport?
So if you were doing an arm, what like the curls,
Bicep curl.
bicep curls, you'd want more blood to go to the arm, so it would stop sending as much blood to say the legs, because a lot of the time when you're doing bicep curls you need to be sitting down. they would take that blood and push it more towards the bicep.
Good. So you've got the process, or you told me why, which is correct, but it doesn't just push it. How does it happen? How do we distribute that blood flow? Because you're right, we want more
Through
blood
the
flow here,
arteries.
and it is the arteries control it, but how? The arteries
To
don't just say,
pump
stop
the
going
blood.
there and go here.
The heart pumps blood to different areas. through
It
the
does,
aorta.
but they're all, imagine they're all roads that go everywhere, and they're all equal roads. How do we stop?
They make the artery smaller in the area they want to remove blood from, so that they can't keep sending it there, so that it goes to the
Good.
place that they want it to go, where they make the artery bigger.
Good, I like that. Do you remember the terms though for getting bigger and smaller?
It was
No.
vasodilate and vasoconstrict.
Constrict. Good. There's a lot of terms that we've gone through today. Vasodilate, dilate to get bigger, and vasoconstrict. Just be careful, Jemima, we don't stop the blood going elsewhere, we just reduce it. So we will still need blood in our legs. We can't stop the blood flow.
Yeah.
So we're just going to reduce it, never stop
I'm
it.
just going to stop the blood going
Yeah,
from my
I
legs.
still
thought
want blood
I might
at
go
my
with
legs.
this awesome fashionable purple colour today.
And I'd like to keep my legs so they need blood flow. Okay, explain for vasoconstriction. Explain for vasoconstriction and vasodilation. So I've written this wrong. Explain how vasoconstriction and vasodilation allow redistribution of blood flow to the digestive system during exercise. What's it asking?
I'm not sure.
Explain how vasoconstriction and vasodilation allow redistribution of blood flow to the digestive system during
Oh,
exercise.
so
It's fasting during exercise.
if you're doing an exercise, it might constrict where the digestive is and dilute where the whatever muscles you see.
Yeah, the digestive system when we're exercising isn't really that important.
I
We're
thought
not
it was. Oh, never mind.
Go on.
I read it wrong.
It's hard. Sometimes it's being
I
able
read it really
to
odd.
interpret the questions is sometimes the biggest challenge, because you know the information, and if I was in your exam to prompt you, you'd know it. So good. We are, for the digestive system, we don't need to break down food while we're exercising. We need to concentrate on what we're actually trying to do, which is our exercise. So we constrict the blood vessels going to the digestive system to reduce the blood flow, and dilate the blood vessels going to the working muscles to increase the blood flow. Explain why redistribution of blood flow is beneficial for the performer as long as they haven't eaten recently.
So that they have more energy and endurance in the exercise that they're trying to perform.
Perfect. They'll be able to create more energy. The oxygen is used to create energy, which we'll look at in detail later. But the more oxygen they have, the more energy they can create, therefore the longer they can work for.
Is that where, you use the example of not eating an hour before swimming? So the consequence of having blood divert to the digestive system means that's why you get cramp.
Yeah, because it'll have
there's
less
not
there.
enough.
I don't think that actually will come into specification at all, but yeah, you don't want to, if you've just eaten, there's going to still be blood flow going there because it will need to break it down. So therefore you're going to be less effective because some of the blood is still helping with digestion opposed to focusing on just the exercise that you're doing.
What is it that happens with the muscles when you get cramps?
Good question. It won't come into the specification. Like spasms of the muscles, but it'll look at A level. I don't even think you go over it into A level. I teach the psychology side opposed to the science at A level. But it'll be linked to the salts and nutrients in your body. But you won't have to go anywhere near that. That's quite complicated. Number 8. Which chamber of the heart receives oxygenated blood from the lungs? Read again. Which chamber of the heart receives oxygenated blood from the
Arteries.
lungs? Which chamber?
Read that question.
What's chamber?
Oh, left atrium.
The left atrium on this side. So careful, that's what we need to stop in exams. Go back and read the question. Explain the role of the vena cava.
Pushes the blood into the heart.
So the role of the vena cava is to transport the blood back to the heart. So it's the main vein in the body. What is the formula that explains the relationship between stroke volume and cardiac output?
Oh, it was stroke volume times the other thing. What was? Oh,
Cardiac.
it's the HR.
Not yet.
It's like
Heart-
HR thing.
Heart rate,
Oh yeah.
because it equals cardiac output. So stroke
Oh.
volume times by heart rate equals cardiac output. The amount of blood you pump per beat times by the number of times it actually beats will equal how much blood you have in a minute.
Bless you.
Okay, I'm going to do a few more questions, but just to go over the homework first. The homework questions are on Dropbox, but I've also emailed it to you all as well. So you've got some exam questions. I want you to do those exam questions without any resources. So if you want to go back and read through all your notes first, read through it first, and then do your homework questions, because I want to use it to check understanding. The homework questions go through this lesson, the muscular system and the skeletal system, so it's a mix of all, and they're all exam-based questions. I also want you to do a bit of pre-learning for next lesson. So the next lesson is going to be the respiratory system, and it's on pages 31 to 33 in your book. But the three areas that I want you to look at are the composition of inhaled and exhaled air, so what's inside the air that we inhale and what's inside the air that we exhale. Two key terms, just like stroke volume and cardiac output, but this time with the respiratory system, vital capacity and tidal volume. And lastly, the structure of the respiratory system. So when I say structure, if I was talking about the structure of the cardiovascular system, it'd be being able to label the heart. I don't expect you to know it all, but just have a read through so you've got a basic understanding, so when we go through it, it makes it much easier.
I like these post-it notes, they're nice and big.
Yeah, they're really good, I like them. What is this on the board?
So hard.
It is the heart. Tell me about it, Jemima. Tell me about these arrows. Go for it.
The blood goes through the inferior and superior veins into the right atrium.
What is that vein called?
Vena cava, sorry.
Good, that's right.
Into the right atrium, through the tricuspid valve into the right ventricle, through the pulmonary valve, out of the pulmonary artery into the lungs. Then it comes through the pulmonary veins with oxygenated blood into the left atrium, through the bicuspid valve into the left ventricle, out of the aortic valve, and then into the rest of the body through the aorta.
Good, perfect.
I
You
did
hate
that
this,
really
don't you?
fast.
It's because Jemima's just got it. Not everyone will get it like that, don't worry. Do you want me to go to the one with the codes?
Yeah.
Yeah?
Bless you.
It goes into the what's it called the superior and inferior, then
Vena cava,
vena
perfect.
cava, then down into the right atrium, and then
Through the
the tricuspid valve,
good, into the
the right ventricle,
ventricle, good.
and then through the pulmonary valve, then through the pulmonary artery to collect oxygen from the lungs, and comes back through the pulmonary veins,
Good, into the
the left atrium, down into the
bicuspid,
bicuspid valve, down into the left
ventricle,
ventricle, and then through the
aortic,
valve, and then through the
aorta. Perfect. What I want you to do, so sometimes the heart is drawn like this. Sometimes it's not. Sometimes it's drawn in another way. Sometimes they're going to draw it just like this. So 4 boxes. So on your piece of paper, nice and big, I want you to draw the 4 boxes.
Oh god.
Now label those 4 boxes. This is the heart, so what does each box refer to? Because sometimes you'll see this in exam, this is the heart. It'll say, what's this one, what's this one, what's this one, what's this one? How many chambers are there in the heart?
4.
So what are these? The top 2 are the atriums,
Atrium.
and the bottom 2 are the ventricles.
So left ventricle.
Good, so this will be the right atrium, right ventricle, left atrium, left ventricle. Now add your tricuspid and your bicuspid valve. Where would they be? So feel free to draw it, the 2, like a door, if you want to draw it. So I would draw my tricuspid valve here, and my bicuspid valve here.
Oh.
Oh, I did this quite big. Never mind.
It doesn't matter how big you've done them. And now I want you to add your vena cava. So vena cava goes into what chamber?
Right.
Right
The superior
atrium.
or the inferior?
Depends on how you've drawn it. I draw maybe anyway. Superior and inferior.
Oh, I've done my face.
If you're not happy with how you've done it, you've got more paper there, you can change it. So we need to make sure when we're drawing this that the arteries and the veins are going from or to the correct chambers. Because now we're going to add the pulmonary artery. So which chamber does it come from?
The right ventricle.
Good, so it's going to come all the way from here. And this will be our pulmonary artery. If we've now got our pulmonary artery, what valve can we add in?
Pulmonary valve.
Pulmonary valve, so that's here at the beginning, isn't it? Here's the next one, okay. So we've got our vena cava, we've got our pulmonary artery. We're going to come back in now through the pulmonary vein. Where are we going to draw that?
Into the left atrium.
Into the left atrium, so it's got 2, doesn't it, the pulmonary vein? What artery are we missing?
What artery?
Yeah, what artery have we not drawn on there yet? That big one.
Aorta.
And which chamber does that come from?
The left ventricle.
Good, it's aorta. That nice big round one. Gonna come here. And then what can we add if we've now got the aorta? What valve can we add in?
The aortic.
Aortic valve, which is here. So you need to be able to, for the exam, be able to label a kind of really basic drawing where they'll literally draw 4 squares and expect you to understand that valve must be the tricuspid or bicuspid, or a more complex picture of the heart. Let me just close this so you can't see. Okay, turn everything over so you can't see anything you've got. Just going to go back to the picture of the heart again. I want you to be able to label the heart without looking at anything else. Remember, it didn't have the inferior vena cava. It doesn't have the inferior vena cava on it. You had to draw the arrow, remember?